Okie dokie. So here we get to talk about friction. So friction you've definitely heard in the English language and probably used that word yourself. We can describe it as two surfaces moving relative to one another will experience friction. Friction can be defined as a force that resists relative motion. So here's an example of static friction. Your teacher is pushing on a desk and feeling particularly wimpy that day, so he can't actually move it. So the desk is sitting here on the floor, and the teacher is pushing in this direction. So we could say that there's a push in this direction, and because he's not actually moving it, there is friction in the backwards direction, and the frictional force would exactly cancel out the push. This is called, because the surfaces are not moving relative to one another, and so the surfaces we're talking about are the bottom of the desk and the floor. So these are the surfaces. The surfaces are not moving relative to one another, so we call this static. Oh wait, it's written right there. Okay, so we call that static friction. If the two surfaces are moving relative to one another, so here, teacher's been working out, draw some muscles in there, and the teacher pushes on the desk, and the desk slides along the floor. So as the desk is moving, the desk has some forward momentum. Okay, so this is not a force, it's momentum, which we will talk about in great detail. So I'll say movement. But once he lets go, there's no force in the forward direction. Okay, so I'll write this. Force, there's no force pushing the chair forward, but there's definitely a frictional force in the backwards direction, so friction slows it down. You know from living on Earth for quite some time now that you get an object sliding along the floor and eventually it will come to rest. So that's due to this frictional force. And because the two surfaces, so we have the chair and the floor, because the two surfaces are moving relative to one another, we call it kinetic friction. So two surfaces moving relative to one another. All right, and we'll get to that down there. All right, so what affects the force of the friction? Two things. One is the stickiness of the two surfaces. So if you've been to an ice skating rink, right, you can walk out onto the ice skating rink, and it's quite slippery. If you're on ice skates, it's even perhaps more slippery. So here's ice, and here's shoe, and it would be slippery. And that's just a function of the two surfaces together. So slippery, or maybe you have the experience of driving, right, when it's all icy outside. So the stickiness of the two surfaces, and again, that depends on the two surfaces together, right? If you have if you have chains on your tires, the stickiness increases between the chains, the tires, and the ice. And then the force pushing the two surfaces together. So I think the stickiness makes sense intuitively, but we're going to call this the coefficient of friction. So yes, in physics we can use a number to quantitatively describe how sticky two surfaces are relative to one another. And then the normal force is the force, right? You've learned before that this is perpendicular, but it's the force pushing the two surfaces together. And it makes sense that the more you push the two surfaces together, the more friction there will be. For example, here's your teacher trying to push on the desk, and the students are laughing at him. And then some kid comes and sits in the desk, right? And now they're really laughing at him. Ha ha ha. Because he definitely can't move. Ha ha ha. Definitely can't move the desk, because with the kid sitting in it, there's even more downward force, and thus normal force. So the force pushing the two surfaces together is greater, and the force of friction would increase with more weight. I'm trying to write weight, but the app's lagging. Okay. So I think that this probably makes sense, right? You push the two surfaces together. You could try rubbing your hands together and you push more, and you're going to feel more heat because there's more friction. So that situation in formula form looks like this. And I like how physics kind of takes this common sense and puts it into mathematical language. We can say force of friction is equal to, and this is the coefficient of friction, so a measure of how sticky the surfaces are relative to one another, coefficient of friction, and I'm just going to abbreviate by stickiness, and normal force, you have learned that is perpendicular to the surface. And we'll say push together just to help us remember what that means. This says together here. Push together. Okay, so we're going to do a little practicing with calculating force of friction and how that works in different situations. Coefficient of friction, let's talk about that briefly. So mu, this is called mu. You hear how I pronounce that? Mu. It's not a U, it's not a U with an elephant trunk. It's a mu. It's a unitless quantity. So when you look at, if you have 50 newtons equals mu times 80 newtons, do you see if we divided both sides by newtons, we'd end up with just some number. So mu is a unitless quantity. And it's usually between 0 and 1, just in terms of practical values. A value of 0 would mean absolutely no friction, and so that's pretty ideal. 1 is like super sticky race car tires or climbing shoes or something like that. I mean, you could talk about, like duct tape on duct tape, and that would be greater. Usually the coefficient of static friction is less than the coefficient of kinetic friction. So this is why anti-lock brakes, I'll write that in words. I mean, anti-lock brakes serve more than just that purpose. But the idea behind anti-lock brakes is here's the icy surface. We'll draw that in blue. Here's the icy surface of the road, and here's your car, and here's the deer. This is an awful deer. There's a tail. Okay, here's the deer that runs out in front of you, and you're slamming on the brakes, and you don't want to slide. And so if you lock up your brakes, these two surfaces are moving relative to one another, and you'll actually get less friction. And so the idea behind anti-lock brakes is the tire senses when the tire is locked up, and then it releases some braking pressure. So the idea is to get the tire and the road not moving relative to one another. Because 1, you actually get more friction, but 2, you can actually steer. And you can steer around the deer, and the deer lives. Yay. Okay. So we'll do a demonstration in class where we have, this is a classic physics thing, an inclined plane, and a block sliding down the inclined plane. And what we can do is we can actually get it where the block is not moving, so it's at rest because it's sticking, but then you give it a slight nudge. So you give it a slight nudge, and what happens is it starts moving, and it will actually accelerate down the ramp because the force of friction has decreased. So here, when they're not moving, the force of friction is enough to keep it static. But once it's moving, the force of friction decreases, so it actually speeds up. So we'll see that, and it'll be amazing. On your formula page, this is the way that formula for force of friction is written. And all this means, so absolute value meaning if the force is in, the frictional force is going to be positive, basically. You're never going to have friction kind of helping, reduce the force required to move something. The little arrow up above indicates that it's a vector quantity. Vector quantity. And here's mu. And then the frictional force is less than or equal to. I think I can give you one example and that will make perfect sense. So frictional force is less than or equal to. So if we go back to this situation where, and I'll redraw it, desk, teacher, okay? So the teacher's pushing on the desk. And let's say, you know, this is something really heavy, 100 kilograms, massive, excuse me. And let's say we calculate the frictional force, and what we get is 1,000 newtons. Okay, so that's a large force. It's about 200 pounds. If your teacher is only pushing on the desk with a force of 5 newtons, right? He's feeling particularly wimpy that day. The desk is not going to push back with a force of 1,000 newtons, right? It's like he pushes this direction with 5 newtons and the desk goes flying that way. That would never happen. So frictional force is only going to act with the amount of the applied force. So if the physics teacher pushed with a force of 5 newtons, friction would push back with a force of 5 newtons and the thing wouldn't move. It's not going to move until the teacher pushes with a force greater than 1,000 newtons, but friction only pushes back with a force equal to the applied force. Okay, bunch of words, but that's where that less than or equal to comes from. Let's take a look at the next page. Okay, so some calculations. So we have this situation. Here we go. Physics teacher again pulling on a 10 kilogram box with a force of 50 newtons. It's sliding along the ground. And this right here, mu sub k, meaning coefficient of kinetic friction, is 0.2. Something between 0 and 1. All right. So we're going to figure out a bunch of things related to this situation. First of all, what's the mass of the box? So that's given to us. And I frequently write mass and weight next to one another and ask you to write them down or calculate them so that you really gain an understanding of how they're different. This box has a mass of 10 kilograms. Its weight is the force due to gravity. And so we calculate this from W equals mg, where on Earth, the acceleration due to gravity is 9.8 meters per second squared. So we end up with the box having a weight of 98 newtons. So before we talk about normal force, let's draw a free body diagram. So it's sitting on the ground, physics teacher's pulling on it, and we kind of expect that it's going to move. So we have this force, and what was that, 50 newtons? Yeah, 50 newtons. And the weight is pushing downward, or gravity is pulling downward, excuse me, with a force of 98 newtons. And maybe to be more precise, we would draw these arrows to scale. So you see how the 98 Newton force is greater, longer arrow? And so the ground is going to push up with a force that's equal to this 98 newtons. How do we know that? Well, the box is sitting on the ground. If the box were sinking into the ground, we would know that the downward force were greater. And if the box were levitating up in the air, we would know that the upward force is greater. But because the box just moves side to side, if at all, we know that the upward and downward force cancel. So physics teacher is going to pull to the side, and there's going to be some frictional force, but we don't know that yet. So I'm just going to make kind of a random arrow. I'm assuming the box is going to move, so the frictional force will be less than the 50 Newton applied force. Here's our free body diagram. Notice how we didn't draw the floor, we didn't draw the physics teacher. It's just the object in question and the forces acting on it. Okay, so based on that, I think these are going to start to make more sense. So we know, so you have that in front of you, right? I'm going to zoom in over here. The normal force on the box, so this is perpendicular to the surface, meaning perpendicular to the floor, 98 newtons upwards. Just to keep us organized, we might draw little arrows indicating direction. The frictional force, so this is where we're using this formula. Frictional force equals mu times the normal force. So our coefficient of friction is 0.2. Our normal force is 98 newtons. And we get a frictional force of 19.6 newtons. And if you were drawing an arrow next to that to indicate direction, remember, frictional force is, in this case, in the backwards direction. Okay. Now, net force. So again, difference between net force, and people get confused because they see that N. This is normal force, perpendicular to surface, but net force is, it's the result of all the forces acting on the object. So in the up and down direction, these cancel out. We don't have to worry about that. But in the horizontal direction, it's going to be 50 newtons minus whatever the frictional force is. So this is why for net force, I have 50, this is indicating it's in the horizontal direction, 50 newtons minus 19.6 newtons, so that equals 30.4 newtons, and if we were drawing an arrow to indicate direction, we know that that is to the right. Okay, so that physics teacher is pulling with a force greater than the frictional force. And lastly, to find how quickly the box accelerates, we're using F equals ma, where the F in F equals ma is the net force. That's what actually ends up going towards accelerating the box, and so we have a 30.4. We could maybe make arrows. This is an A right here. So 30.4 newtons equals mass, 10 kilograms times acceleration, and we end up with an acceleration of 3.04 meters per second squared, and that would be to the right. Okay. Free body diagram, we have that over here. So I think we're good on that one. Now it gets slightly more involved when the applied force is not perfectly perpendicular to the surface, when the force is not horizontal. So here we have no longer a 50 but 100 Newton force, and it's applied at a 30-degree angle, and here we could say with respect to horizontal. Remember that? Okay, so I've worked out the SOHCAHTOA. You just have to know how to do this. Don't say you hate SOHCAHTOA and call it good. All right, learn it. Ask questions. You can do it. Here's our triangle. The 100 Newton force is the hypotenuse. This is a 30-degree angle, adjacent side, opposite side. So we can say cosine of 30 degrees is adjacent over hypotenuse, and sine of 30 degrees is opposite over hypotenuse. So we get these two numbers. This is how much it's being pulled to the side, and this is how much it's being pulled up. So side and up. It's obviously being pulled to the right and up, so we figured out those forces. So I'll write those here. It was 86.6 newtons to the side and 50 newtons up. Notice how these numbers do not add to 100. This is a Pythagorean theorem. A squared plus b squared will equal c squared. Okay, so what are we finding? Weight of the box. We know the mass is 10 kilograms, so the weight is 98 newtons. And let's put some little arrows to indicate direction. Horizontal component of pull, that's what we just found. How much is it being pulled to the side? 86.6 newtons. Vertical component, so it's being pulled up. It's not going to go off the ground because it weighs 98 newtons, but it's being pulled up 50 newtons, which is, about half of the weight of the box. So when we talk about normal force, this is the force of the ground acting up on the box. We definitely want a free body diagram. So let's think about this. Here we have the box, and we have pull. So let's go 86.6 and 50. All right, newtons. We know that we have, so that's due to the pull. We know that we have, I'm trying to draw these to scale, 98 newtons, that's the weight. So Earth pulls downward. We know there's going to be some friction. We don't know what it is. And then there's one more force, and that is the normal force. So the floor pushing upward on the box, F sub n. So if we consider the vertical, so forget about side to side, just look at the vertical forces. We have 98 newtons downward, we have 50 newtons upward, and we have something else. So because the box is not flying into the air or sinking through the floor, we know that these, the up and down or vertical forces, are balanced. Therefore, so hopefully your brain is like, well, I think the normal force would then be 48 newtons. And your brain would be right. That's good. So this is because 48 plus 50 equals 98. And we could be more specific and say the vertical forces are balanced, meaning they cancel each other out. They end up in the vertical direction, giving a net force of 0 newtons. So this is where this math came from. Normal force, 98 minus 50 is 48 newtons. Okay, and remember, that's what contributes to friction. So when we go to frictional force is coefficient of friction times the normal force. Notice how the fact that the pull is being, it's being pulled kind of up and right, the fact that it's being pulled up slightly means that the frictional force is actually reduced. So we end up with 9.6 newtons of friction. We could write that in here. 9.6 newtons of friction. So that's pretty small relative to the other forces acting on the box. And we need some arrows to indicate direction. So frictional force is backwards, and the normal force was upwards. All right. Notice if we look at these arrows, 48 and 50 up, 98 down. And then when we talk about net force and direction, this is pull to the side, and this is friction pulling back. So we have 86.6 pulling to the right and 9.6 pulling back. Those are in opposite directions, so we subtract, giving 77 newtons, and the direction looks like to the right. So the net force is what goes towards calculating acceleration in Newton's second law. 77 equals 10 times a, and so we have an acceleration of 7.7 meters per second squared. So I made a little note here, and that is to compare to, if you look at the example above, right, it was a 50 Newton force instead of a 100 Newton force, but even if we double the acceleration to account for the fact that, for example, if the top example were 100 newtons, so I'll draw this, 100 newtons, that would give us this for acceleration, whereas when the 100 newtons was applied like this, it's pulling less to the side, but because it's pulling up, it's reducing the friction, and so we get a greater 7.7 acceleration than 6.08. Thanks for listening.